last session for the day. And this session is about climate resilience, challenges, and new perspectives. It is organized by Ignacio Segovia Dominguez from the NASA Jet Propulsion Laboratory and the University of Texas at Dallas. To you, Ignacio.
Thank you so much, Monica. Welcome everyone to our last session of today's TIAS annual meeting. As mentioned, this is session number 4, climate resilience, challenges and new perspectives. We encourage every speaker to take around 20 minutes for their talk, such that we can have 5 full minutes for questions. And we have 3 speakers today. Without further ado, I leave the floor to our first speaker, Devan Becker from the Wilfrid Laurier University in Canada. Welcome, Devan.
Thank you for that introduction. Can you hear me okay?
Yeah, we hear you very well.
Good. All right. Sorry, I'm a little bit sick today, so if I mute myself randomly, it's just a cough. Anyway, today I'm going to be talking about some statistics and some data science topics regarding ignitions and burn areas in space and time. So I'm looking at wildland fires in British Columbia. So what I'm going to talk about today is 2 models I did during my PhD, one that was mostly temporal and then had some aggregation in space, and then one that was mostly spatial and had some aggregation in time. Then I'm going to talk about a little data science application that kind of bridged them a little bit together, and then I want to talk more generally about what research I would like to have done, either by myself or some other people in the future. So the temporal model is, again, it's British Columbia in Canada. British Columbia is split into 6 regions that are for administrative reasons. So each of these has its own fire management crew that fights fires that occur in any given area. So that's the reasoning for keeping that as these very large regions, and that's going to come up. These are quite large. Region 5 is, I think, bigger than Spain, I think I calculated. So like this is not a small little area. But the general idea of my work, I'm not going to go into too much detail because I want to talk about broad ideas afterwards, but the general idea is that I've got a model for the size of fire J in region R on day I. So I've got these 3 subscripts, day I, fire J, region R. It's some sort of log normal distribution with a mean. Each region has its own variance. The mean is based on some covariates plus a random effect. This random effect is also in the model for count. So that's a shared random effects model. The count is just the total number of fires on day I in region R. So it's the sum of indicator variable for fires in region R day I. I have here a Poisson. I'll talk about what ended up happening to it later, but again, it has some generalized linear model structure with a mean based on covariates, as well as, again, this random effect. This random effect changes from day to day, and there's this linking parameter to allow for, say, if BI is 1, that means that there's 1 extra fire expected compared to what we would expect from the covariates. That doesn't need to mean 1 extra hectare burned. So 1 extra fire can be associated with 3 extra hectares burned, or 0.1 extra hectares burned. We've got that scaling difference. I want to talk a little bit about covariates and AKA features, depending on whether you're talking to somebody from statistics or computer science. For the count model, I used, they had to be aggregated to the region level. Again, some of those regions are very, very large, so aggregation is going to lose a lot of information, especially if I want to use something to do with weather, some function of weather that gives me some information about the fire conditions on that day. It's not going to be ideal, but it's what I wanted to use the fire management zones because of who's actually fighting these fires is consistent. I also have the fire load, so the number of other fires burning on that day in that region. So fires can burn for multiple days. So there might be some holdover fires in the same region, and that will affect how much resources they have to fight new fires that happen on that day. And I've got a spline smoother just for the time so that there's a seasonal effect. So you can expect more fires different parts of the season. For the size of the fires, the covariate is measured at each fire at the time of ignition, or which may be estimated, which is another source of potential variation. The fire weather index variables are engineered features based on weather, so they're based on physical models of fire growth. They're intended to capture, they're intended to transform the weather into something that's important for the people managing the fires. So they're things like the buildup index for how many leaves and branches that you expect to be dry on the ground, how deep it goes into the ground, and all those sorts of things. I also have fire load and, again, a spline smoother for time in the size distribution. With a shared random effects model, what I'm really interested in is this linking parameter gamma. So if I have a positive random effect on a given day, that means in the count model, which doesn't have the linking parameter, if the random effect is positive, then there's going to be more fires in that area. If the random effect is negative, then there's going to be fewer fires in that area. But with the size model, which has the linking parameter, if the random effect is positive, but the linking parameter is negative, then what's happening is we're going to expect extra fires on that day, but we also expect them to be smaller if this gamma is negative, if the linking parameter says there's a negative dependence relationship here. And so that's kind of that was the overall goal with this research. Everything else was just trying to fit the best model to the data. It wasn't a super easy challenge. Looking into the data, I looked at how many of the fires were exactly 0.1 hectares. And up until the year 1984, 75% of all the fires were 0.1 hectares. And then after 1984, only about 50 were exactly 0.1 hectares. It was remarkably consistent up until this time. And then suddenly it switched, which I think was they started doing aerial surveillance and doing a slightly more specific than 0.1 hectares. I think they might have changed to, they changed to saying 0 hectare fires. They started allowing people to record it as 0 hectares. And so that was an administrative change that affected my data. The other thing that happened in my data is up until the year 1975, most of the fires were recorded as 0.4, well, not most of the fires. Out of fires that are 0.3, 0.4, or 0.5 hectares, most of the fires were recorded as 0.4 hectares. And then after 1975, we slowly built up to most of them being 0.5 hectares or 0.3, and very few of them being 0.4 hectares. So what happened here is we switched from imperial to metric. So 0.4 hectares is 1 acre. And so that's the imperial measurement that they would just guess 0.4 hectares, or they would just guess an acre. And now once we're in metric, they're guessing half an acre or half a hectare. And then 0.3s are probably more accurately 0.3. So 0.5s could be pretty accurate or could be a guess. 0.3s are generally going to be 0.3s. So what I had to do with the response in this data, so the actual fire size is one of the responses, I had to have a multiple coarsening model where the model it was a mixture model of coarsening of 0.5 could mean 0.45 to 0.55. It could be somewhere in that interval, or it could be 0.25 to 0.75. It's two different forms of rounding. Whereas something like 0.3, that's always going to be that 0.25 to 0.35 rounding. And so it's censored within those intervals. So the log normal distribution that I used was actually quite prescient because this became a survival analysis, and there's software readily available to do that. Some other aspects of the model that I'm going to gloss over, but were a lot of work, is instead of a Poisson distribution, there was 0 inflation, or 0.1 inflation, rather. We also included 0.1 inflation, and there was over dispersion, so it did 0 inflated negative binomial model. which is similar to a zero inflated Poisson model, but as if it has yet another random effect inside the model. I also, since I have 6 regions, I can say that the regions should be generally pretty similar overall, but with random deviations. So that's a hierarchical model or a shrinkage estimator. The random effects, I used an autocorrelation model that said that the random effect on one day was probably going to be similar to the one on the day before. This random effect is assumed to be something driving fire's behavior, and that should vary relatively smoothly. And I mentioned the spline terms for seasonal effects. Jumping right into the results, estimation was done in INLA, if anyone is interested. That allowed me to do, oh no, for this one it was JAGS. This one was JAGS, so that was Markov chain Monte Carlo with Gibbs sampling. So the results were really interesting. It actually, I stared at my computer screen for at least 2 minutes trying to figure out what was going on here. It was very clear that person-caused fires, that linking parameter is positive. So an increase in the count is associated with an increase in the size, and a decrease in the count was associated with a decrease in the size. This is sort of the behavior I expected, so this wasn't super interesting to me. Lightning caused fires, though, it was negative, and it was consistently negative, and there were very few models where it turned out to be positive. So this is saying that if my count model is saying that there's going to be extra fires in a given day, it's also saying that they're going to be smaller. So one of the, this seemed really counterintuitive for a while, but then I realized that lightning caused fires happen during rain, and rain makes fires smaller. So if we expect a lot of lightning caused fires, it's because we expect a lot of lightning. And if we expect a lot of lightning, it's because it's going to be associated with a lot of rain. And if there's a lot of rain, then fires are going to be smaller. And this isn't being captured by my weather covariates. For person-caused fires, it's sort of the opposite situation. If I expect a lot of person-caused fires, it's because there's a lot of human activity. And I should mention that person-caused fires isn't just campfires going out of control. It also includes railways, a train going down a railway track and causing a spark that starts a fire, or forestry operations starting a fire. So forestry operations, especially if it's a really good day for cutting down trees, it's also a good day for those trees to burn and to cause, so more fires should be associated with larger fires as well. Moving on into space, we're looking at a continuous space model, but in this case, just 1990, all fires that happened in 1990, they tended to happen, if you're not familiar with the terrain of BC, there is a mountain range going through here. I think there's a mountain that goes in between these two locations here, and a little bit more mountainous over here. There's mountains just everywhere. It's a great place. But in 1990, we tended to have a fair few fires near Vancouver, and some fires out in this Kelowna, Canmore area, and a little bit north of those places. If I look at the size of the fires, so these dark colors mean that they were small fires, and the light colors mean that in this region, the fires tended to be larger. We do see that sort of dependence relationship where there were a lot of fires this year here, and they tended to be small, whereas there were fewer fires up here, but they tended to be big. So we're seeing that give and take, there's a little bit of a relationship going on there. So I fit a very similar model. It's still a count model that has something like a Poisson distribution, except in this case, it's log Gaussian Cox process. So it's based on the integral of the exponent of a Gaussian process over a region. So any region that we want to draw, we can find out the expected count based on this Gaussian process. It's also based on covariates as well as a random effect. A log Gaussian Cox process has to have a Gaussian process as part of it. That's why it's called a log Gaussian Cox process. So this random effect has to exist and only exists in the model for the count. And then I've got the linking parameter again and the shared random effect. And you can see the shared random effect. The size model hasn't really changed. It still has the shared random effect, except now that shared random effect is continuous in space. And the other thing that has changed is now the linking parameters in the count model. It used to be in the size model. It's in the count model just so that if it gets estimated as being 0, this term can disappear while it's still being a log Gaussian Cox process. So the covariates that I used for this, for the size model, I'll just cover this quickly. It's the same as before. I have the same fires. It's based on the same data set, so I can fit the same sort of model. I just have a different structure for the random effect. For the log Gaussian Cox process, I needed covariates that were spatially referenced and constant over the course of a year. So I've got elevation and distance to highway or railway, which I'm looking at lightning and person-caused fires separately in this analysis. So that's important to note. Lightning-caused fires shouldn't really be affected by where the railways are or where the highways are. The results, just jumping forward, this is the one I used INLA to estimate. The results, so here's this continuous random effect for log Gaussian Cox process, only part of it, and we see that it covers, this was, I think, for 1987. I took these from 2 separate publications, so sorry that the dates don't match up. But there were a lot of fires in the far southeast, and a couple in that area that's north of Kelowna, Canmore, a couple near Vancouver, and some in Vancouver Island. But then there's also this shared random effect, which is saying that there are also some fires up here. We just didn't see them because they don't show up in the log Gaussian Cox process random effect, because the shared random effect covers that for it. So these, in this area, we had more fires and they were expected to be larger. So we got this dependence in the north, and after looking through 50 different pictures, I kind of eyeballed that, yes, in the north, that's there tends to be dependence in the north. But for lightning-caused fires, I also got distance to roadways as a significant covariate, which is interesting because highways shouldn't cause lightning-caused fires. That shouldn't have an effect. There are 2 possible explanations for this. One of them is that over time, the significance decreased, so it wasn't as big of an effect, or the effect size decreased, sorry, which indicates that it might be a problem with detection of the fire. So we might have just not noticed ones that weren't close to the roadway. So we only saw the ones that were visible from the road. It might also be that pollution from the roadway is causing cloud formation above the roadway and causing more lightning. That's another option for what might be happening. And the third option is that we might have just built roadways where lightning fires tend to happen. It doesn't need to be causal. But I did this same model for 50 different years, and that's a lot of results to look through. And that's why I switched to, where I turned to image recognition, specifically non-negative matrix factorization, which is something that tries to learn parts of an image based on a large collection of images. So given a large collection of faces, it seems something like in this, building block that it found, there's part of a mouth. In this one, it's some part of maybe a nose or something in this one. This basis function represents certain amounts of eyes, or certain represents a certain type of eyes. So the original image looks like this, using just the features that it learned and some some coefficients for how much of each feature to use. It can recreate the original image. So what I'm interested in is what features did it find? What patterns tend to happen throughout? And I should mention that it's non-negative, which means that all of these are additive. So if it uses, say, this building block that shows eyes, it can only add that. It can't add these eyes and then subtract part of these eyes to try and tweak it to get it the right way. It can only add things. So any patterns I see in this, these building blocks are patterns that actually exist in my data, which is why we chose this method. I'm going to skip over this. So I'm going to run back to this. I'm treating this as one single image, so I'm looking for patterns in both at the same time. And that was some research needed to be done for that. Here are the results. I'm going to highlight a few quick ones. Just some of the bases had nothing in the shared random effect and just had, I like this one. It kind of looks like the fire emoji, which was a very nice little thing to show up. The ones that did have patterns found in the shared random effect always in the north. So basis 1, basis 2, basis 5, and basis 7 all had patterns noticed in the shared random effect, and all of them were in the north. And so that sort of helps with interpretation of these models. I'm going to skip over this one, I think, because I want to talk more about the features. So looking back on this work, I did this doing a pure stats PhD, and I've since done a lot more data science and machine learning sorts of things. And I realized basically what I did was I had a goal in mind, and then I had a bunch of feature engineering and response engineering, which is a term I made up. I don't know if that's something people say. So feature engineering, fire weather index on its own is a sort of engineered feature. It's based on a physical model made by Mike Watton and some other physical scientists many years ago. Fitting those seasonal effects, a spline term is something like an engineered feature that we get to say that there are patterns in certain areas, and then the model determines how much to use those patterns. We are inputting these patterns into the model and letting the model choose them. And that's a sort of thing that a lot of feature engineering is based on. Fire load was something I had to create based on other information in the data that could have been available to a model that used the total number of fires in a different way, but it was something that I had to personally say, this is something that's important, you should look at this. I had to process the data myself so that the model could see this information. Weather effects across—
Sorry, we have 2 minutes.
Oh, sorry. Okay, thank you. And distance to road were also things that I had to input into the data. Response engineering, I had to change what my response was based on coarsening intervals, aggregation of counts, which is a potential issue with modifiable aerial unit problem, and zero inflation is also part of that. I'm going to skip, since I've only got 2 minutes, I'm just going to skip to the end. I basically want this talk to encourage other people to look into how should we engineer features for this sort of spatial data. Should we use something like convolutions, which do edge detection for our covariates that extract extra information from them? There's a lot of research now on how to extract information from our covariates in different ways. We can talk about one-hot encoding, we can talk about smoothing, we can talk about imputation. These are all forms of feature engineering. Lots of the models that I've seen for forest fires, especially, all do a different sort of feature engineering, and they all seem like they're reasonable, but there's no general guidelines for somebody else who wants to pick it up. What should they do to get interesting features that will inform their models? So this talk is just a call for research into reasonable approaches for a general framework for feature engineering for forest fires. And so that, sorry for having to skip a few slides. I would like to acknowledge CANSI, NSERC, and ICLR for funding various projects shown in this research, and thank you all for listening.
Thank you so much, Devan. We have time for one quick question, if anybody from the audience wants to ask. Okay, if not, one quick question. Have you linked these findings with any colleague of government or someone in the government that actually could help you to have some sort of impact on policymakers?
A lot of this research was done with, I mentioned Mike Watton. I've presented this to him. He's the one who did most of the pioneering work in feature engineering for forest fires. It was based on deterministic models. Deterministic physical models. So I've talked to him about it. Dave Martell is also somebody who's deeply entwined in research and with the government. I've got contacts in the government that I've talked to about these sorts of things, but there's still no momentum for a consensus on this sort of thing. Yeah.
Got it. Excellent.